your number? Oh, okay.
All right. Hi. Welcome all to the first interdisciplinary seminar in the ECE department. Thank you all for coming. It's a pleasure to have among us Dr. Raginsky. Maxim is currently at Duke University. He received his PhD from MS, in fact, a BS, MS, and PhD from Northwestern University in Illinois. And he was a postdoctoral researcher in the Center for Photonics at Northwestern. He's subsequently in pursuing quantum cryptography and quantum communication and information theory. He subsequently joined the Beckman Institute, where he was a fellow, where he carried out research also in information theory, learning, and computational neuroscience. He's now, as I mentioned, starting as a research scientist at Duke University, starting this fall, and where he'll be involved also in learning and statistical signal processing. And his research interests are very broad, including, as you will see today, when he's talking about sensor networks. And it's a pleasure to have you here. Thank you for coming.
Thanks. All right, thanks. So you can hear me back there, right? Oh, okay, great. So let's see. So this is joint work with Avon Fernandez and Todd Coleman at University of Illinois, and it's like it says here, it's a low complexity universal scheme for rate-constrained nonparametric regression in a wireless sensor network. And it's a profusion of terms, but I'll explain all of them as the talk goes along, and it'll be fairly easy to see what's going on here. So is this the button that?
You see that little
Oh, yeah.
Could you guys please turn off your cell phones, please?
Let's see. There should be stuff here that I can use. Oh. No, that's not it. Oh, there it goes. Yeah. So, sensor networks is kind of a new exciting medium and a way to think about collecting large amounts of data from various ecological or natural military applications. So, for example, you can imagine something like measuring underwater temperature in some geographic region in an ocean. So you would have an oceanographer dropping in a bunch of temperature sensors. Is there? Well, I can use one of these as a pointer, I guess.
Yeah, you can use that.
So
you can actually even write on that.
Right. So using a bunch of sensors, dropping them in, they're going to measure temperature. So the typical setup would have. Oh, I'm sorry.
Yeah, you have to put the pen back.
Oh, really?
Yeah. Just
wow.
put it down.
New stuff. Okay. So. Yeah. So such a sensor network would have a bunch of sensors that are dropped in here, and these show wireless links between them. They can talk to each other. Then there's going to be a relay node, which is maybe floating and floating around, and the sensors will relay their measurements to it, and then it'll transmit them to the base station or fusion center. So you would have your scientist sitting somewhere on the beach and taking these measurements. So how will it look? A typical sensor, a typical sensor, for example, is characterized by two things. So where it's located, so this is a sensor I, for example. It's located in some coordinate xi, and it gives you a measurement y sub I. And this measurement y sub I is related to temperature, but there's also measurement noise and other reasons, so a lot of other ambient noise. And so this x sub I and y sub I are correlated, and y sub I is somehow related to temperature, but there's noise. And then the fusion center will somehow will receive these xy pairs from all the sensors and try to reconstruct what the temperature distribution is in this region. So how do we do this? in statistics, classically, there's... It's really taking its time.
You may want to use just the mouse.
Yeah.
Up there.
Where is that?
It's on the desk there.
Oh, is it a wireless mouse also?
No, it's not a wireless mouse.
Oh, well, okay. I'll just stand here then. Why is it taking me back? Oh, right. Because I'm used to a Mac, only one button. So classically, you would have a what's called a regression problem, where you have a bunch of observations of two related variables, x and y, and you really want to recover the relation between x and y. So in this setting, x could be the location of a sensor, y could be the noisy measurement of the temperature at that location, and you want to be able to have a function of location that accurately predicts temperature at that location in say mean square sense. So which is why, having observed this data, say n samples, you then construct a function f from the domain of x to the domain of y, such that it's a good predictor of temperature in this mean square sense. And to guide your search for this function, there's an interesting property that says that, suppose I pick some candidate function, f, and I say, let this be my predictor. Then you can exactly write down the mean squared error as a sum of two terms. One term, and that would be this one, depends only on the distribution of x and y. And this eta of x is actually the conditional expectation of y given x, and it's called the regression function. And the remaining, whoa, this is all going to be taped. Nice. And the remaining term, the one I highlighted in red here, and I'll do this too, that depends on the function f. So really the best least squares predictor of y from x is this regression function eta. And if you're off from this function, then this is the additional error you're going to incur. So really this problem, we can reformulate this by, in the following way. You have to use the training data, this sample, to approximate or to learn something about this eta, and then take that approximation as your predictor. This is, however, what you would call a centralized setup. It's not really suitable for describing a sensor network yet, because here we have two basic assumptions. One is we're seeing all the data at once. And two is we're seeing them exactly. In a sensor network, however, these two assumptions may be violated. Because sensor networks operate on a power budget. You drop in sensors, for example, if it's some hostile environment, maybe you're measuring concentrations of some toxic chemicals. You won't be able to get in there and replace batteries in these sensors soon, or maybe at all. And so you have to conserve power. So you state this by basically saying that it costs power to send 1 bit over 1 meter over a wireless channel. So the sensors basically have to compress their observations in some way to cut down a number of bits they need to communicate this data to the fusion center. So this, of course, places some problems at our in the hands of the designer. So first of all, this compression must have low complexity, because again, sensors it may be cheap for the sensor to do some computations locally, but they have to talk to each other a little bit, and that also costs power. Secondly, because compared to the setting of the previous slide, you're going to see some compressed summary of the data, your regression estimation will not, in general, be as accurate as if you had the data uncompressed. And thirdly, what we really want is, we want a universal scheme. We want a scheme that sort of comes out of the box and works, because in many situations you may not be able to accurately describe what's going on, how the noise is affecting the sensor measurements. There may be some environmental influences you're not really aware of. So all these three things have to be taken into account when designing a sensor network, distributed realization of this regression problem. And so some previous work, of course, there's quite a bit of work done in this domain. The earliest approaches took this, what's called distributed source coding. They say, okay, let's assume that two sensors at two locations, their measurements are correlated. Let's model these correlations in some specific way. And then one sensor can use the fact that its measurements are correlated with the other to reduce the amount of communication it needs to do. This is aimed at having very low complexity schemes. These distributed source coding schemes are such that sensors ideally don't talk to one another at all. They don't cooperate. They just somehow compress their measurements and transmit them to the base station. On the other hand, these approaches typically are non-universal. You assume that you know a statistical model for of what you're sensing beforehand. And furthermore, they're parametric, meaning that typically you assume that the correlations between neighboring sensor measurements are, say, Gaussian with specific covariance structure. So it's described by a few parameters, and you design a code matched to these parameters. So that's not really what we want. Another kind of schemes is taking ideas from wavelet estimation, where you adapt to various discontinuities and breaks in the underlying field. And so really guide the estimation based on the features of what you're estimating. This approach, so this one is by Nowak and others. Unfortunately, it has fairly high complexity because multi-resolution methods, when you apply them on the sensor network, you have to have a lot of hierarchical communication between sensors. And sensors also have to cooperate to do fairly sophisticated model selection and fitting. So that's not so good. On the other hand, it's universal. So this approach can in principle work for any noise model under some conditions. And it's what's called nonparametric, meaning that unlike the Gaussian case, you make very minimal assumption on what the relationship between sensor locations and measurements is. Typically, you would say, oh, it's a smooth function. It has some derivatives that are bounded or something like that. And you find a best estimate of the regression function in this infinite dimensional class. So that's these two are very desirable properties to have. A very recent paper by Wang and Ishwar proposed a very nice algorithm that uses distributed estimation with sensors that only send a single bit to the fusion center. And it's very low complexity. They don't talk to one another at all. However, it has a big disadvantage of being non-universal. So the way they set it up is that you know that your noise is bounded. So it has bounded dynamic range. And you know that dynamic range. And in some situations, it may not be an accurate assumption. It may be bounded dynamic range, but you don't know the bounds. You don't know how large the noise is. In some situations, it could be some Gaussian noise, and it's unbounded. So you want to account for that. And also, their approach only works for sensors that are just dropped in uniformly at random within some region. But on the other hand, it's also non-parametric, just like the multi-resolution estimation. So what we have developed is an algorithm that kind of trades off between the last two approaches. So it uses some very interesting novel combinations of ideas from information theory and non-parametric estimation and learning, and it's characterized by the following four statements. First of all, it's low complexity. Sensors do talk to one another, but not too much, and they don't have to do any sophisticated function fitting or anything like that. They just exchange simple messages. And to compress the data, they use something that's very, very common in signal processing devices called uniform scalar quantization. It's used in analog to digital converters, for example. You can just buy these things. Secondly, it can support very, very low communication rates. So these quantizers that they use, they can be very, very coarse. And interestingly enough, we show that the degradation of performance is minimal compared to having precise uncompressed data. And you can actually quantify this the amount of this degradation. And with sufficiently many sensors, you can achieve performance as if you weren't compressing. It's universal. It's this algorithm that just works for any distribution of sensor locations and measurements, provided that the regression function exists. And finally, it's also non-parametric. It can handle a wide variety of these infinite function spaces and even achieves optimal performance on standard spaces. So we'll discuss that as well. Oh, I'm going in the wrong direction. So you have to list various assumptions that you make. So our assumptions are as follows. So suppose that n sensors are dropped in at random over some, say, we'll model this as a unit cube in some dimension d. Typically, it's 1, 2, or 3. I mean, you're sensing either on a line, some terrain, or you're sensing in space or underwater. This density of deployment doesn't have to be uniform. It can be anything. Can even be unknown. Secondly, the fusion center knows where all the sensors are. So once they're dropped in, they can do some triangulation and figure out their locations. And we also assume that each sensor knows where it is. It doesn't know where the others are. So each sensor makes a real number measurement. And this measurement is related to its location probabilistically. So there's noise. A typical example is when you have what you're measuring is some function of location, such as temperature or pressure or concentration of a chemical, and on top of that there's additive noise. Typically, you assume it's Gaussian with some variance, and it's independent of x. And this is just notation. So this boldface y denotes the vector of sensor measurements, and we're going to assume that sensors are what you would call statistically exchangeable. That I put sensors when I drop them in, I put them independently. I don't put the next sensor based on where the previous one was, and given this, their measurements are independent. So all the correlations that that could exist between neighboring values are, for example, encoded in this function f if this model is accurate. So these are the assumptions, and oh, right. The system just won't give you a break, will it? Okay, now what? Let me close this thing. There. Well, look here too.
Maybe the arrow, the double arrow there.
This one?
Yeah.
Oh. No. The system is more trouble than it's worth. Oh, come on.
I think that writing thing will go away.
Oh.
Okay. There you go.
Wait, what am I doing here? I'm sorry about that. All right. So here's what the scheme will look like. This is very abstract description, and I'm going to describe each one of these components in great length. So first of all, and this is crucial, we allow the network and the sensor to share some, additional random vector. So the fusion center will generate some random vector and beam its components to the sensors. So this u sub I is this random number given to sensor I. On the network side, then there'll be encoding. So the sensors will take their locations. They're allowed to use them. They'll take their measurements, and I'll take this randomized, this random vector, and they're going to output a binary string. We don't constrain the length of that string. So this denotes the set of all possible binary strings. So once they output this binary string, we're going to look at its length in bits, and typically you want to look at how it scales with the number of sensors. So you normalize this by the number of sensors. And then the network communicates this binary string to the fusion center. Then the fusion center will have a decoding function. Again, it knows where the sensors are, so you can use this information to help it decode. And it has this string that it receives from the sensors, and it has this common randomness with the sensors. So it produces an estimate of the sensor measurements. So this y hat is the list of all estimated sensor measurements. And finally, once it has this information, these x sub i's and y sub I hats, it then uses this as data in a regression estimation procedure. So that's how that works. This is the ingredients of the scheme. So what are we interested in? we're interested in two things. One is how many bits on average do we send out? And we're going to look at the expected number of sensors. So this is the encoding of the sensor locations, measurements, and the common randomness with the fusion center. And we average this over these random variables. And secondly, we're interested in the mean squared error.
So, excuse me.
Yeah.
So what does U live? Is it in Rn?
It's an R. Well, the bold U, yeah, it's a vector.
Okay.
Yeah.
But in R, right?
In R, yes.
Yeah.
It's a real valued vector, yes. And we're going to, in fact, describe it explicitly. And then you're also interested in the mean squared error between the actual oh, wow.
Yeah, you're not.
How do I go back? Nice. Okay. Right. So if you remember the previous slide about the regression function, you remember that this is the error due to misestimating the regression function by some f hat. So we really care about this because the other term is constant, depends on the distribution of x and y, is not under our control. This is under our control, and we're going to hopefully see that this will decay to 0. And we're interested in the behavior of these, the bit rate and the mean squared error as the number of sensors increases, and hopefully we'll see the trade-off. Yes?
So I would like you clarify the kind of the communication scenarios. So you said you assume sensors gonna talk with each other, and also you assume the fusion center gonna send this vector U to all sensors.
Yes.
Okay, so then the question is, are you also assuming every sensor gonna receive the same vector or not?
Well, I mean, this it doesn't have to send it to them. For example, they can have random number generators, and the fusion center can keep track of, and different sensors will have, for example, different seeds. And the sensor fusion center can have the same random number generator on its computer, keep track of all the seeds for each sensor, and then when they compute the pseudo-random number, they'll get the same vector. Does that clarify it? That's, I mean, this, when I explain where this randomization comes from, I'll also say that typically this U is assumed to be pseudo-random. There's a random number generator at each sensor, and the fusion center knows the details of each of these random number generators. And so there really doesn't have to be a communication of this U to the sensors.
The question is, when you generate these random seeds, so if you use a random seed just for a specific sensor, so every time when you rotate or you select your random seeds, and then you can have like different random vectors or the same random vectors. You really don't know, and you cannot tell whether, for example, the received vector, for example, is U. Okay, so received.
Oh, you mean by the network?
Not by the network. Let's say by the sensors. Because this vector actually is sent just from
over a
the
wireless
fusion
channel.
center to sensors.
Yes.
Okay, so you never know actually
Well,
which
on the other hand,
sensor gonna receive
on
what
the
kind
other-
of vector.
On the other hand, typically you can assume that the fusion center has a lot of power to waste, so it really can put in a lot of power in that message and so break through the wireless channel and send it. We're going to abstract away from this communication channel issue. Finding a good way of sharing this U, for example, like I said, sensors are, when they're manufactured, they'll come with a seed value. When you buy them, you'll see that seed value, and then later the sensors can keep track of local time and add this time to their seed value to reinitialize the random number generator or something like that.
What I really mean about this question is because you are talking about the universal scheme,
Yes.
and this universal scheme, it depends on where the regression going to be performed. Whether the regression going to be performed at the fusion center or the
fusion center, yeah.
Yes, and then but also when you do the decoding actually is done at the sensor.
No, the decoding is also done at the fusion center.
So the sensors are just dummy sensors sending bits.
They're not. I mean, as far as their communication to the fusion center goes, yes, they're just sending bits. They can exchange integer values or they can exchange analog messages with each other, but as far as the fusion center goes, yeah, they're just sending bits to it. There's no decoding done by the sensor network. So the U will be used both by the sensors and by the fusion center to encode and decode, but there's no decoding done by the network itself. Does that help?
Well, I think that pops up
So it's
other
not
questions.
different, it's just one.
Well, let's see how the scheme operates. So encoding and decoding will basically have two parts. Encoding will consist of what's called the dithered uniform scalar quantization. So each of the sensors will do this thing on its own and output an integer index. Then the sensors pool these integer indices in a certain way, talking only to their nearest neighbors, to come up with the overall bit string. So each sensor receives some information from its neighbor, uses this information to compress its integer index into some bits, and then sends these bits out to the fusion center. So this is a decentralized adaptation of what's called it's called Ziv's scheme. And Zamir and Feder actually kind of enhanced it, and we're going to use their enhancement. And then the estimation will be performed using a series estimator, and I'll explain what it is. But the decoding will be done by the fusion center. Sensors just send bits. So this is the architecture. So maybe this will help. You have sensor locations. So for example, sensor 1 is located at location x1. It makes a measurement, outputs measurement value y1. Then there's this common random. I didn't touch it.
No, you can't touch it. It is annoying.
Sorry. These random numbers, they're like I said, they're shared between the sensors and the fusion center, but they don't have to be. I mean, I shouldn't have said that they have to be communicated by the fusion center. There can be a synchronized random number generation there without communication. The point is that each sensor will add this random number to its measurement, and then there's going to be some encoding. The encoding will produce three things. This M is the quantizer index, so that'll be explained later, but it's the index of the interval that the measurement plus noise ended up in. And the K and the L are discretized versions of the sensor locations and of this random signal U. These are discretized so that you can feed them into this universal lossless code, which only works for discrete data. Oh, that code, that's the communication between neighboring sensors. That's where that is going to be. And then, so assuming that this code is lossless, of course, and so this fusion center will be able to get these M's exactly. So then it sends these M's through decoders, gets an analog value, subtracts off the noise, this random noise, and gets the y hat values, and then it uses these y hat values together with its knowledge of the sensor locations to estimate the regression function. So let's see what exactly the details of all these boxes are.
Yeah, apparently you can do it in just click in the white region.
Yeah, oh, that's true. I can just do this, can't I?
Yeah, it's not going to do it when you want it. Just click twice in the white region.
Yeah. No, once was enough. So here's what uniform scalar quantization of dither looks like. It's very standard. So you fix some epsilon a priori. So larger epsilons will correspond to lower communication rates. And so sensor I, it has a random variable uniformly distributed minus square root of 3 epsilon, square root of 3 epsilon. And this is called a random dither. And we assume it's independent of its location and measurement. And it's also known at the fusion center. Like I said, when you buy a sensor, you can have a random seed already printed on the box. The sensor basically adds this dither to its measurement and then encodes it like this. Basically, this is your real line. It partitions it into intervals of length 2 to the square root of 3 epsilon. Then if this is your random dither, this is your measurement. They're added together, they end up here, and so you're going to quantize it to this point. So you divide this by 2 to the square root of 3 epsilon, and your index is going to be 2. So each sensor does this, and you get this vector of integer indices.
So what is, intuitively, what is the usage of U? What do you use it for?
Basically what that does is this y hat is going to be, when the decoder reconstructs y hat, is going to be First of all, you can write it as y sub I plus some error, and this error is independent of y, and it has fixed variance and zero mean. So this really facilitates getting efficient estimators of various quantities.
But you have noise also.
Yes, yes.
Outside this thing.
Well, I mean, the noise, the y is noisy. It's related to So it's an interesting thing. In many situations, apparently in distributed scenarios, you have to add noise to sensors.
For sensor I, you have two parameters. X is the coordinator and
Yes.
yi is the measurement.
Yes.
And now you are saying y sub I is the noise. So
No. It's related. This measurement is noisy. So when you suppose a sensor is just measuring temperature, if there was no noise, this y sub I would just be a function of x sub I. But typically, there's going to be some probability distribution of y sub I given x sub I. That accounts for noise. That's what I mean.
So there is noise, and he adds on top of it this sort of.
Yeah, I add noise. I deliberately add noise at each sensor.
This artificial noise.
And right, and you'll see why it's needed. So and this is, by the way, this is a very standard algorithm. It's called Ziv's algorithm, and just we implement it in a decentralized way. So once this list of indices is obtained by the sensors, at this point, each sensor knows only its own index, m, and it knows only its own location and its own measurement. So now it has to communicate this m to the fusion center. And how do you do that? You want to reduce the number of bits. So because of this statistical exchangeability of sensors, there's going to be some redundancy in these m's. There are going to be repetitions and regularity. Typically, if there was arbitrary communication allowed between the sensors, then they could use, if there are sufficiently many of them, they could just talk amongst each other however they want, and remove this redundancy by estimating the probability distribution of this m.
Ask about this question, because when do you say redundancy, what do you mean? What kind of redundancy? Is the, for example, we are measuring temperature. So for example, my reading is 76.
Yeah.
So, and your reading is 78. So what do you mean by redundancy?
By redundancy, I mean the following. If there are going to be some regions that are fairly homogeneous, and so they're going to have fairly similar temperature readings. They're going to be quantized to some indices. So, and they could be interspersed, for example, with regions where the temperature all of a sudden drops or falls. Drops or rises. And so, if there are regions of homogeneous temperature, you can actually replace that with, for example, by saying, I measured this temperature 78 10 times. So instead of compressing 10 78s, you just compress 78 once and compress 10 and then send that. That's what I mean by removing redundancy. It's sort of like flipping coins. If I have a coin and I keep flipping it many times, there's going to be redundancy in the sense that the probability of getting heads is approximately going to be equal to the fraction of getting heads in that sequence. That's what I mean by statistical redundancy.
The redundancy actually can be reduced by just transmission. By just reduce your transmission, because as what you said, if I got 78, okay, for 10 times, I just transmit 78 and 10.
Oh, yeah, exactly.
Okay,
sure.
But then that has nothing to do with other sensors, and that's not.
What do you mean? See, each sensor takes only one measurement, so the redundancy is going to be across space, not in time. Each sensor takes only one measurement.
Right.
So this redundancy is in space, not in time.
I think that's exactly what I want to clarify. If you're saying in space means, for example, you got 78, I got 76, I still don't know exactly what you mean by redundancy. So for example, if you want to reduce the transmission, let's say suppose you quantize, you quantize the time, right?
Yes.
So for example, you suppose, let's say I transmit 78 every second. Okay, so let's say suppose you transmit 78 every second, I transmit 76 every second. So as what you said, for example, you have 10 measurements, all of them are 78. Then what you gonna do?
No, what do you mean you transmit 78 every second? You transmit only one measurement. per sensor. But the measurements across different sensors are correlated somehow because of, they're sensing a common environment. That's where the redundancy comes from. It's from the fact that I'm here and you're here and some other guy is here. We're in a relatively homogeneous region. We're all going to get 78. That's what I mean by redundancy. Not the fact that you send 78 every second. We're not taking multiple snapshots in time of this temperature field. We're just doing one measurement.
In that case, why? If that's, I think that's exactly where's the point. So if you are saying the homogeneous actually space, for example, V3, all of us, for example, we detect 78. So then that means as long as this measurement of 78 is transmitted, it doesn't matter who transmits. As long as this information is transmitted, then the fusion center can get the information. So
well, the fusion center still needs to know what measurement came from what sensor, though.
Actually, when you guys are going to meet right after this, maybe you can take that up.
I think there's some, yeah. So, but the point is that let me just quickly write this down. So this is going to be a long string of measurements: M1, M2, Mn. These are the measurements of the sensors. By redundancy, I mean that because these measurements are obtained from a similar statistical model taking place at each sensor, these variables are independent and identically distributed as well, actually. And for that reason, because they're independent and identically distributed, the approximate frequency of each value of m is going to be well represented. Is going to well represent the probability of that m. Well, that's what I mean by redundancy.
okay.
Okay, so in information theory, then this is how lossless compression, for example, this is how WinZip operates. It finds redundancies and removes it. Like I said, if the sensors could talk to each other any way they wanted, they could reduce this redundancy down to what's called the entropy. So the entropy of m. But here they also have the side information x and u that they can use to further remove redundancy. Because if you know something that's correlated to your information, you can reduce the amount of bits you need to communicate it even further. So the optimal description length that you could achieve is the conditional entropy of this m given x and u as side information. And we want the sensors to talk to each other just a little bit. We don't allow arbitrary communication between sensor 1 and sensor 100. But we want them to talk to each other a little bit and try and get the average number of bits that they send out to be approximately equal to this. And so we're going to then use what's known as a lossless code to approach this performance as number of sensors goes to infinity. And we're going to implement this with low communication complexity. So here's how we're going to do this. First of all, like I said, the x and u are continuous quantities. You want to discretize them to find a statistical model for m's. So here's one way that we develop for discretizing them. I don't have a solid theoretical justification for this, but I'll explain why it works in practice, and it does work in practice. So assume that sensors can pass messages to their neighbors. Then they can use a standard protocol for finding extremum in a ring. So, if they can talk to their neighbors, you can assume that they're in a ring. And this can be found using about n log n message passes. And then they communicate this minimum value and maximum value to the fusion center. Alternatively, they can clip their observations within some interval, and sensors whose observations are outside, and we assume, and hopefully there will be few of them, they just say, oh, I don't send anything. Forget about me. So either you do this or you do that clipping. And then, so you say, let n be basically the number of integers between m min and n max. And now you're going to take your observation region and partition it into n squares. And then each sensor, since it knows where it is, it can compute the square that it's in. And you also do the same thing with that interval that the random signal is drawn from. So you also partition it into the same number of subintervals. And if sensor I has u sub I, what? It reads my mind, unfortunately incorrectly. If sensor I has its random noise, with its random dither, in this, say, interval 13, then it's going to compress it to k equals 13, and here, for illustration's sake, L equals 24. So for each sensor, we discretize their location and their random dither to these integers that take values between 1 and n. And so far, the sensors only talk to their neighbors. Next, so here's the main idea of how they are going to compress these m's into bits. What you really want is, so a sensor can, if it knows what the previous sensors have, assume we order sensors according to their distance from each other. So if each sensor knows what its the previous sensors had observed, so this is their actual integers, so they're numbered from 1 to I minus 1. It knows their k values, and it knows its own k values. It can try and construct a probability model and predict the probabilities for each possible m. It knows its own m, and therefore, once it constructs this probability model, it can then use encode the actual m using, say, a Huffman code or an arithmetic code, and get this many bits approximately. So minus log of the probability that it predicted. So for this sensor sensor I needs the k, l, and m counts of the sensors before it. And our adaptive method for choosing n basically makes sure that these counts are not too sparse. If you so this is our justification for doing this adaptive discretization. Suppose that I get n possible values for the sensor indices, for the quantizer indices. If I discretize my space of x's and u's too finely, then this information will just overwhelm the counts for m, and therefore I will basically use very many bits to describe it because I'll assume it's uniform. If it's done too coarsely, then the counts again won't be accurate. So we say, well, let's balance the number of values that the indices actually take with the number of values that the site information can take. And you'll see from the actual form of the counts why this helps. And so once this is done, this is the total number of bits that the entire network sends in. So for a given value I, this is the length of sensor I message to the fusion center. And because the fusion center basically knows these m and k and knows the k and l values for each sensor, it knows which probability model they use. It knows which code they used for their which code each sensor used, and it can decode them using the same code. So that's the idea. Yes?
Remind me what K and L here.
Yeah, K is the discretized version of this additional random noise, this U, and L is the discretized version of the sensor location. And M is the quantizer index of each sensor.
So do you assume a conclusion tree or some structure there?
Yeah, it basically is a tree. Yeah. So what happens? Well, I mean, it can be a tree or it can be like this. So assume that sensor I knows the indices of its predecessors. Then it estimates the conditional probability that it'll get measurement index A given these as follows. So this is the typical conditional probability formula. But here this p hat kt, it's called a Krzyzewski-Trofimov estimator. And you can define it recursively like this. So the first sensor just assumes that every possible index is equally likely and is going to send the most bits of anybody. And then you see that you can write for each subsequent sensor, you can represent its estimator in terms of estimators from the previous sensor. So it just sends its k and l values to the previous sensor, and the previous sensor recursively computes this and outputs this probability vector for all possible a. And then the second sensor then, aha, I have this one index, so I encode it using this many bits. So therefore, you can compute these estimators very efficiently using some sort of recursive message passing. Or if you allow sensors to just send messages, then you can do this in a tree. So this is a way to do this entropy coding, to pool this information, remove redundancy with only neighbor-to-neighbor communication. So it's fairly low communication complexity. If you want to do it this way, you only need basically n rounds of communication. Okay? So once this is done, the fusion center receives these bits, and B sub I is a lossless binary encoding of the quantizer index M sub I, and it's been compressed enough that the fusion center that knows these, and these can just recover M sub I, and the number of bits is small. Once it gets to M, it decodes M, basically just finds, yeah, right. And I was, but then I forget to put it back, and so the sensor, so the fusion center takes the index from the ith sensor, just converts it to the midpoint of the corresponding interval, and subtracts off their random noise, this additional deliberate noise. So this is where you really need this randomization. First of all, we know that these y hats are independent and identically distributed because scalar quantization. Each sensor quantizes these things independently. Secondly, what's called additive noise model is valid. So the quantized representation of y hat, is y plus additional noise, where noise is independent of all the y's. Its mean value is 0, given the x locations. This is actually our our modification of Ziv's arguments, because he's not conditioning and we are. And its conditional variance is epsilon. It's independent of the number of sensors. It's independent of the distribution of x and y. It's constant. So once the fusion center gets these y hats, it can then we were just talking about that. Incredible. Okay. So the fusion center just does the following. So we assume that this regression function exists and is square integrable with respect to this sensor density x, px. And so there exists some Fourier expansion for it. We can pick a basis, phi sub j. We can, pick some sort of wavelet basis or trigonometric or polynomial, whatever we want. And so this function will have an expansion in this basis. And basically we do, standard series estimation. We choose cutoffs j sub n. So we're going to keep only j sub n plus 1 terms, such that this limit is 0, so that you'll see why that's necessary. For example, you can take square root of n as the cutoff. Or there's a nice adaptive way of choosing cutoffs based on the data, and I'll show you how that works. And for each j, you basically estimate this coefficient theta j by doing the standard thing, because this is the each theta j is an expectation of y times phi sub j of x. You just approximate it by its average, and then form the estimate of this form. You just take your theta hats and add however many of them you have computed. So this is the scheme. Let's look at its performance. First of all, how many bits are you sending out? Well, so Ziv's scheme comes with a guarantee. We have, because we use side information x, which is the locations of the sensors. This is the limit of the bit rate, ideally. This is what you would get. You would get this number, which depends on the distribution of y and x, depends on epsilon, plus an additional penalty due to the fact that you're doing scalar quantization. And this penalty is less than a bit per sensor. This quantity r y given x, it's called that's an object from information theory, and it's called a conditional rate distortion function of y given x. Basically, it quantifies the following. If I knew x, and somebody gave me some sort of a description of y, which also could depend on x, then this conditional rate distortion function quantifies the amount of mutual information this description of y, w, has to have about y, given my knowledge of x, for me to be able to have least square, mean squared error between y and w to be within epsilon. So this is kind of abstract, but for a standard example where y is given by a function of x plus Gaussian noise in this way, the conditional rate distortion function is actually given by this. It's just, it's very simple to see. If you know x and you know f in this particular situation, you can just subtract off f of x, and all you need to compress is this noise z, and this is basically the rate distortion function of the Gaussian random variable of mean zero and variance sigma squared. And this holds regardless of f. So this is this. So, but in general, if I have some sort of distribution of x and y, what I can guarantee is that in the limit, my number of bits coming out of the network is no more than this. So this is the best I could do anyway in compressing y with a knowledge of x, plus additional penalty for doing scalar quantization. And this penalty is constant for whatever distribution. Then I'm interested in the mean squared error. So this is the regression function. This is my estimator. And this mean squared error looks like this. This is the estimation error. And as you can see, it depends on epsilon linearly like this. So if epsilon, this quantizer resolution, goes to 0, I get something that is the performance of the scheme without compression. Then there's the cutoff here, of course. And this term goes to 0 by my assumption on the cutoff. And then the rest is basically the bias I get due to estimating this regression function by cutting off the series at some point. And this quantity, of course, this goes to 0. And so this entire sum goes to 0 as well. And these constants depend only on the distribution of x and y, and on the basis they don't depend on n or on epsilon. So the reason why this works is precisely because of this random dither that I add and subtract. My estimators of the coefficients are going to be unbiased and efficient. Well, rate efficient at any rate. It means that the expectation of theta hat is theta, and the variance of theta hat goes down as 1 over the number of sensors. This is the best you can get, the convergence rate 1 over n according to the Cramér-Rao inequality. So the only penalty I pay due to quantization is basically this. And if I have a huge number of sensors, I can easily overwhelm this. And this use of random dither is absolutely essential to get this. If you don't add randomization, you're going to get a biased estimator, and its variance is going to be actually dependent on where exactly on the line you are. But this random dither gets rid of that problem in a very nice universal way for any distribution of x and y, I must add. So, for example, this Ziv scheme, that's the beauty of it. It works for any distribution of x and y. Well, Ziv only considered distribution of y. He assumes no knowledge of x. We specialize it it's not trivial to specialize it, but if you do, then you get this. For any distribution of y and x, you get this. And here, for any distribution of y and x, you get this nice mean squared error performance. In particular, some statisticians like to characterize estimation procedures in terms of minimaxity. They say, well, suppose my regression function is in some, nice function class, such as in this model you have function plus additive Gaussian noise, and x is one-dimensional. Suppose f is such that its rth derivative is Lipschitz with some constant alpha here. And statisticians say, okay, well, if my regression function in this class, and this is all I know, then I can look at the worst case function in this class, so hence the supremum over the f in this class, and then I find the best estimation procedure for that function, and I see what its mean squared error will behave like. And so in this case, if this parameter beta, which is r plus alpha, the technical condition, is greater than a half, then you get this lower bound. So this is the best performance on a worst case function in this class. And using the trig basis on the line and this particular cutoff, our scheme yields this performance. It's easy to show. And therefore, we're actually attaining this minimax lower bound apart from these multiplicative constants, which don't depend on n or on epsilon or on anything else, except for a distribution of x and y. So we're really in good shape here, according to this criterion. So this kind of validates the usefulness of our approach. And here's a nice way of choosing these cutoffs adaptively. So if you know that your function is in some smoothness class, then by all means choose the cutoff suited to the function class. If you don't, here's how you choose it. You compute any unbiased estimator of the variance of this quantity, and then this is going to be unbiased estimator of theta j squared, and then you just do this minimization. Find the j that yields the smallest value for this sum on the right, and use that j as cutoff. So the rationale for this is that, well, suppose I had this estimator which cheated, and it knew the function beforehand. So if that were the case, then you can write the mean squared error of, well, mean squared error of any estimator with these theta hats looks like this. This is just standard, stuff from harmonic analysis. So this is the error I incurred due to estimating the coefficients. This is the error I incurred due to cutting off the series. You can represent it in this way. So this term only depends on the underlying regression function and is not under my control. But this term, on the other hand, depends on the variance of the estimators and depends on these coefficients. And we assume that this oracle, it can cheat, so it knows what these coefficients are. So it can choose this j to minimize this term. Well, we're going to try and mimic this oracle. So I can estimate this variance, and I can estimate this theta j squared, and which is what I do here. But I can just set some upper bound on j so that because the variance of each coefficient is 1 over n, I don't want to overwhelm that performance with a huge number of terms. So this has to be something that when you divide it by n, it goes to 0. The n over log n is standard in statistics, where if the function is going to be one of those smoothness classes, this thing is going to be greater than all possible cutoffs for those smoothness classes. So you kind of choose it on a conservative side. And in our experiments, we actually use this adaptive method to characterize the... My God, I'm awful.
Maybe you should have an additional thing.
Yeah. So this is one example. So standard kind of a workhorse example where you suppose we're on a unit square. We have uniformly distributed sensors, and there's some sort of so this could be a pressure wave. So the underlying function is this sign. These are the coordinates of x in the cube, and we had Gaussian noise with a variance of 0.2. No. It's x1 and x2. These are the coordinates of. I didn't want to write x1 and x2 because those are supposed to be sensor measurements.
Okay.
So it's not. So these are the x and y coordinates in this cube. So this kind of shows you. This is the underlying function, plotted like this. It's a height plot. These red dots are where the sensors in a particular realization. There are 500 sensors. They use epsilon of 0.2, and this is the reconstruction of the function. So you can see the features. So these peaks and valleys are very well represented. This estimator is kind of bare bones estimator. You typically would do some other stuff on top of it, like thresholding and removing various suspected bumps to even improve this estimator. But this already shows something interesting. So this is a number of bits that the network has sent out for 100, 500, and 1,000 sensors. So this blue curve, that's the conditional rate distortion function of y given x. The dashed green curve is that Zipf's bound, so you add 0.754 to it, and you can see that for high enough epsilons, you actually approach the Zipf's bound with already 500 and 1,000 sensors. Even with 100 sensors, you're pretty close to it. You're slightly above it. So what that means is that you can use very, very coarse quantization. And if you look at the mean squared error plot, so this is 100 sensors, 500, and 1,000. For mean squared error, you can see that even at high values of epsilon, you're still getting fairly good mean squared error performance compared to no quantization. So this scheme can really shine at very, very low rates when the number of bits sent out by the sensor is small, and yet you still get decent MSE performance. To show that we can perform on things that are not standard and tried and true as additive Gaussian noise, we came up with Gaussian echo noise, where instead of adding Gaussian noise, you add 1 plus that Gaussian noise. So it's sort of like statisticians would call this heterosedastic regression, where the variance of the noise actually depends on the underlying signal. And again, the same underlying function, the same distribution of noise. We don't know the rate distortion function for y given x, but we plotted the empirical bit rate curves anyway, and you can see that they're even lower in this case than in the additive noise case, and the MSE curves are also perform fairly respectively. So so this scheme works well. Yeah. Oh, sorry. Okay. Well, we're wrapping up. So I presented an approach which is low complexity, so it just uses some standard scalar quantization stuff and simple message passing. It can support very low communication rates and still have almost no degradation in performance with sufficiently many sensors. It's universal in the sense that it can handle a wide range of measurement noise models, as we have seen. It's nonparametric, doesn't make any assumption in the regression function, and it's rate optimal for some function classes. The MSC converges to 0, as as well as if we could do without noise, without compression. And this is just some future work to improve on the scheme. Sorry for taking longer.
Before I allow some questions in the audience here, let me revert back to NCAT. Are there any questions on the mode side? Okay, I guess not. All right, if not, then are there any questions here? We have just a few minutes for questions. I know there are questions, but when you'll have plenty of time to ask your questions. Actually, the one thing I wanted to very quickly ask, I mean, when you say low complexity, what are you talking about?
Communication complexity.
Yeah, but I mean, what is this something that
quantifiable?
Well, is this something that you're doing in real time, or is it near real time, or is it?
Well,
or is it still in the simulation?
This is still in this simulation stage. We're not implementing this, but it could be done in real time. Yes.
All right. Okay. If there are no more questions, let's thank the speaker again.